Imagine a system that operates flawlessly 99.7% of the time, seamlessly processing high volumes of traffic. But for that remaining fraction of a percent, the service quietly corrupts the data. When software breaks, you naturally expect a trail of evidence. A server crashes, an error log flashes across the screen, or a stack trace points directly to the failed logic. But here, there is complete silence. Investigating this kind of issue exacts a heavy psychological toll. You comb through the source code line by line, reviewing every logical branch, and mathematically, the code appears perfect. The system never outright fails. It doesn't time out. It fires back responses at lightning speed, perfectly formatted, but loaded with entirely incorrect values inside the payload. The most dangerous issues in modern software rarely look like broken code. They behave like invisible systemic ghosts, moving through the infrastructure without leaving a single obvious footprint behind. Look at these two contrasting models. Debugging a stack trace is like looking at the glowing pinpoint on the left. You are told exactly where the structure failed. But reading production logs is like staring at the wall on the right. You are handed thousands of identical gray blocks of text and told a specific anomaly might be hidden somewhere inside. Because server logs are designed to capture every single event, 99% of the recorded data consists of perfectly normal, healthy operations. That routine noise actively buries the critical signal. For decades, the standard response to this problem has been brute force. You open the terminal and you start scrolling, manually scanning lines until your eyes blur. You attempt to manage the flood by writing command line queries with tools like grep or awk, filtering the massive datasets to isolate specific warning flags or timestamps. But there is a glaring psychological trap built directly into that workflow: confirmation bias. To run a manual search, you must define the parameters of what you are looking for. If you only search for the errors you expect to find, you are mathematically guaranteed to miss the patterns you never anticipated. A human-led investigation relies entirely on guessing the shape of the bug beforehand. When a failure defies logic, guessing simply does not work. Deploying AI shifts the focus from reading text to identifying multidimensional patterns across thousands of data points. It doesn't interpret the logs the way a human does. It looks for the mathematical relationship between events. The forensic process begins by strictly restricting the AI's analytical focus. If you feed the algorithm your entire log history, it will lose detail or truncate the output entirely. This diagram illustrates the optimal extraction strategy. The massive timeline shrinks down to a focused 1-hour segment immediately surrounding the problem. This captures a strict batch of under 500 log lines, providing a clean mix of the healthy green nodes and the failing red nodes. Step 2 requires a highly specific prompt strategy. Providing the exact request IDs for both the known good and the known bad outcomes is mandatory for the technique to function. Asking the AI for a generic summary of the logs yields a useless list of unrelated warnings. Instead, you instruct the tool to run a strict anomaly comparison between the two datasets. Resolving an invisible failure requires demanding the exact differences between success and corruption, effectively bypassing the noise entirely. Step 3 tackles the hardest challenge in modern software infrastructure: cross-service correlation. The root cause of a bug is frequently buried in a completely different log file than where the symptoms actually appear. The AI maps timestamps from separate logs onto a single timeline, scanning for temporal collisions. It flags a collision a human would miss, a cache refresh and concurrent read hitting the same database row within a 200 millisecond window. In bad requests, this overlap was present. This is what we call a classic race condition. The corrupted data was generated strictly by a microscopic temporal overlap. Once the AI isolated that specific correlation, a 3-day investigation was resolved in 30 seconds. The failure left no obvious errors because the individual operations were completely valid. The bug relied entirely on a fleeting cross-service timing collision that human eyes are physically incapable of tracking. Once the exact pattern is identified, the fourth and final step is translating that discovery into a concrete search query. This allows you to measure the true scope of the bug, revealing whether you have 5 isolated failures or 5,000 occurring across the network. However, Applying this methodology requires a strict reality check. A discovered correlation does not automatically equal causation. An analysis might flag a massive CPU spike happening right alongside your failing requests. You must apply logical scrutiny to recognize that the spike is a symptom resulting from the bad code path, rather than the root cause itself. Furthermore, the algorithm is entirely dependent on your infrastructure. If your system logs lack foundational context, like unique request IDs and millisecond precision timestamps, the AI cannot correlate the events accurately. Artificial intelligence does not replace traditional observability systems like dashboards and alerts. Those tools are the guards standing watch. AI is strictly the forensic detective you bring in to interrogate the raw text when the guards don't know what happened. By delegating the raw text to a pattern matching algorithm, you eliminate the boundaries of manual scrolling and confirmation bias. An exhausting, days-long search condenses down into minutes of objective